everyone. Thanks for waking up and coming to the morning session. My name is Azi Fattahi. I'm a staff member at Durham University. Sorry I cannot be with you in person. Visa issues. US doesn't like Iranians as much. So thanks to the organizers for organizing the workshop, but also allowing me to give my talk remotely rather than in person. As you can see, I will be talking about what we can learn about the nature of dark matter from galactic halos. In the very front page, you see a dark matter halo of a Milky Way on the right-hand side, as predicted in Lambda CDM, and what a stellar halos around such a galaxy would look like. I will go through some background about the stellar halos and their formation, because I think basically it's a broad expertise in the room on various aspects of dark matter. So we are on the same page. I will start by generally saying what we know about the buildup of galactic or stellar halos in cold dark matter, and then I move on into what the properties of these stellar halos could look like in warm and self-interacting dark matter. And if there's time, I might flash a few slides on some of the new projects that my group is working on. I try to remember, especially mentioning the junior people who have worked on different parts of the results I will be showing today. Starting with the mandatory kind of the slide of what we we think the standard model of cosmologies, which has been very successful to explain the larger scale structure universe. In this model, which is expanding universe, there are fluctuations at the beginning of the universe, which in the matter density, which grow into a more complex structure at late time, as you can see in this image from the Eagle simulation. The initial conditions are usually set by what a CMB tells us about what the initial conditions at the early universe looks like, and the computer simulations can help us to follow the nonlinear growth of a structure from that early time to present day. And this nonlinear growth, the picture we have these days is that there is a cosmic web that emerges with voids and filaments and sheets, and in the intersection of filaments, dark matter halos form. And if you look at a dark matter halo of something like the Milky Way in cold dark matter, it looks like, as I was showing in the first slides, kind of an extended halo with lots of substructures around it. These kind of unique predictions from cold dark matter, which is the formation of this larger scale structure, the hierarchical growth of a structure, and also the existence of low mass dark matter halos, are some of the the last 2-point hierarchical growth of structures, and the number of low mass, or the increasing number of low mass halos in CDM, are the two key points I will come back to as I will talk about the formation of the stellar halos. Because movies are fun to look at, to imagine basically what we mean by this hierarchical growth of a structure and the formation of the stellar halos. This is from the Eagle simulation. I hope it comes through fine on Zoom. On the top right, you see the formation of a halo and its dark matter component. In the top left, it's in its gas, and in the bottom left are the stars that are coming with these dark matter clumps. As maybe I can start from the beginning. You will see that different smaller structures merge together, they accrete to the bigger halo, and as this dark matter halo grows, it grows through the accretion of these smaller things. And these smaller objects, of course, they have the dark matter, but some of them, they do have stars, as we can see in this panel. And as they bring these stars with themselves, they form these extended stellar structures around galaxies, which is what we call stellar halos, which is the main focus of what I'm talking about. This is now just a snapshot at redshift 0 from a higher resolution simulation. These are two on the right. These are the dark matter component in two halos that would look like something like Milky Way and Andromeda. These are two 10 to the 12 solar mass halos. And if we look at the stellar light for the same simulation, the same environment, we see as this extended stellar halo structures around the central galaxy. These stellar halos are faint structures. In order to kind of bring them out, you can see the center is saturated compared to the kind of the main galaxy that we usually astronomers call galaxy, the stellar halos are much fainter and much more extended. Just by eye, you can see the extent of the stellar halos are roughly the extent of their dark matter halo, whereas the galaxy, say the disk of something like the Milky Way, would sit in the very, very center of this dark matter halo. Just to give you a sense of a scale, the dark matter halo size is around 200, 300 kpc or kiloparsec, and the disk of something like Milky Way is about 1020, so 10 times smaller. So this dark matter, this stellar halo is kind of tracing this dark matter growth of the halos, which is why it's kind of exciting to learn about what it tells us about dark matter. The other thing I'd like to point out, it has lots of substructures. Again, I don't know if it comes through fine. You might be able to see there are some shells on this halo. If you follow my cursor, there are some things that look like a stream that are the result of dwarf galaxies that are losing their stars, and they form these streams around these halos. So these stellar halos is basically what I will be focusing on for the rest of the talk. Just to make sure we're on the same page, I will be talking about the stellar halos around objects such as Milky Way. And unless for those of you who work in the subjects, the stellar halos sometimes are referred to the accreted component or ex situ versus in situ. Here I'm only talking about the component that is brought by these dwarf galaxies, which are, I guess, usually called accreted or ex situ component. These are the mass that are brought by accreting dwarf galaxies around the host, and these extended structures that we see. Observationally, we also see this this is just two examples. One is Andromeda galaxy with its kind of, you can see the shells and plumes and the streams around it, and another external galaxy where these stellar halo structures are observed. In the Milky Way, we don't have such a bird's eye view, but we also know about, especially after Gaia, tons of substructures around our own Milky Way. So how are these, how has the stellar halo is built up in these, at least starting with the cold dark matter picture? As I said, I will be at this in the first couple of slides. I will be only talking about the CDM. I will tell you when I'm transitioning into the other dark matter models. Here is just an example from a hydrodynamical simulations. This is from those who are familiar. This is Auriga hydrodynamical simulations, and I go to these simulations and basically ask what is the mass spectrum of objects that have been destroyed and formed these extended stellar halos or these accreted stellar halos. This is just a cumulative stellar mass function of those objects that are destroyed, that you can see that there is about a few tens of objects, fewer of bigger ones, more of the smaller ones as expected in CDM. Are destroyed and form this extended structure. On average, for a reference, the blue line is the stellar mass function of the objects that survive to present day. So they have a bound entity at present day, and in an observational sense, we would observe them as dwarf galaxies today rather than disrupted ones that form the stellar halo. Actually, there are on average more destroyed dwarf galaxies around something like a Milky Way rather than compared to the survived ones, roughly by a factor of 2. So this is a total mass spectrum. One of the kind of first order thing we can ask is what are the contribution of these different progenitors? So any given halo has a few tens of objects that have been accreted to it and got disrupted and formed these halos, stellar halos. We can look at the contributions from different things. One quick way just to summarize the results without going into too much detail, we can ask about how many progenitors or top progenitors we need to form 90% of the mass. So this is essentially rank ordering the progenitors and asking how many we need to form 90% of the mass. If we look at all this mass inside R200, again, I'm talking about just the stellar halo mass. If we look at things inside R200, even though at least a few tens of objects have been disrupted, only a couple, we can see a range from 1 to 10, but on average, around 5 or so is enough to form 90% of the mass. This is essentially telling us that contribution from these bigger objects, or kind of the slightly more massive dwarf galaxies, are way more important than the contribution from the little objects in terms of just mass budget. So most of the stellar halo is formed from these bigger objects. If we look at things as a function of radius, this is even way more different, and there's an interesting reason behind that. This is similar to the left-hand panel, but with the y here, the x-axis doesn't matter, it's halo number. So this is just different. There's 30 halos, and I'm looking at all of them. So the x-axis doesn't mean much. The halo number doesn't mean much. It's just different halos. If instead of looking at inside R200, I look at inside 20 kpc, so this is kind of the inner bits of the stellar halo, it's even fewer objects. It's the same definition of how many significant progenitors we need to form 90% of the mass. Usually only a few, 2, 3 is enough to form the inner regions. If you look at the outer bit of the halo, it's slightly different. More objects contribute to the outer halo. And the reason behind this, because of time, I can't go to the very detail, but basically the reason is the most massive objects, because of dynamical friction, they get dragged to the center, and they are way more massive, and they dominate the mass budget in the center. So in the central bit of the stellar halos, you're basically looking at very few massive progenitors. If you want to look at the smaller bits, we have to look at the outer halo. But this dynamical friction and the inner regions are important because it will come up in the rest of the points I want to make. So just a wrap up of the key points that are needed in order to move forward, because I'm going to talk about other dark matter models. Things to keep in mind is, on average, a few tens of dwarf galaxies form the stellar halo. Well, a few tens above some stellar mass, above 10 to the 5. But the contribution only from a few is important. Basically, if we look at the inner regions of stellar halos, we need 1 to 3 on average of massive dwarf galaxies. By the way, massive dwarf galaxies sounds contradictory, but it's a large mass in large range in a stellar mass. So we are talking about stellar masses of 10 to the 9 or 10 to the 10 when I'm talking about massive dwarf galaxies. So we need a few massive dwarf galaxies to form the inner regions, because the dynamical friction drags things to the center. And on top of that, it has been shown by different simulations, mainly actually using idealized setups of studying dynamical friction, of these big mergers, because now these massive accretions, they look like mergers. These big mergers, the dynamical friction radializes the orbits of these objects, and the inner regions of the halo, actually the orbits on average, are quite radial. This is equivalent of observing something like the Gaia Enceladus sausage in the inner region of the Milky Way, which is relatively radial. So these are important points which will matter for the rest of the talk, to look at the different dark matter models. So we can ask about the alternative dark matter models that have been proposed, actually to resolve usually things like a small scale tension, such as missing satellite problem, or too big to fail, or other sorts of problems for CDM. Some of these alternatives that have been proposed, they affect lower mass halos because they've been proposed for that reason. So it's kind of very natural to ask, if the stellar halo is forming from these dwarf galaxies, if you alter the properties of these dwarf galaxies, the properties of the stellar halos would change. But in what way? And I want to highlight that what I will be showing is a work led by a former student in Durham, currently a postdoc at Leiden, Victor Foruhar Moreno, who's been working with Alice Thiessen and I, and a master's student I had, Fergus Henstrich, who's going for a PhD somewhere else. So most of the results that you're going to see about the stellar halo in different dark matter models has been led by these two junior people working with us. Starting with some of the key differences between these different dark matter models that could affect the stellar halo properties. Starting with warm dark matter, depending on how warm it is, but generally it suppresses the power at small scale, which means the abundance of low mass objects goes down. There are some delays in the formation of lower mass halos and lower concentration of dark matter halos. So basically changing the abundance of dwarf galaxies, if you want to say, in warm dark matter is an important thing that could potentially affect the stellar halos. Visually, what it could look like, these are just the same halo, same initial conditions simulated with CDM and a CDM and a warm dark matter framework. As expected in the CDM, where there are powers on much smaller scales, smaller subhalos form and get accreted to something like the Milky Way. This is a halo of something like a Milky Way from a pulsar project. And the warm dark matter counterpart. Hopefully it's clear that some of the warm dark matter one looks smoother because the suppression of power on small scales and the lower abundance of smaller dark matter halos means we don't have tons of substructures, or at least fewer than CDM. Sorry, I'm looking at my phone to check the time. And then looking at self-interacting dark matter, I will talk about the results I'm going to show is a self-interacting dark matter model where the power spectrum, at least on the scales relevant to low mass dark matter halos and dwarf galaxies, the power spectrum is not changing. So the abundance of low mass objects in isolation doesn't change between SIDM and CDM. But the SIDM, because of the thermalization that happens due to interaction between dark matter particle, it affects the internal structure of low mass halos and make their dark matter density profile in the center shallow. This is the same halo we saw in CDM and WDM now in SIDM. It's constant cross-section of 10. I get to that later. But visually, actually, even by eye, we can easily pick up, we can see these two substructures are exactly in the same locations. Some other ones you can trace by eye that the substructures are there. But what is changing essentially the internal structure of these substructures. So these are the key differences. I'm going to kind of turn into what the stellar halos around these look like, at least visually. CDM, well, it's CDM. The warm dark matter one by eye, kind of hard to see the differences. Maybe you can convince yourself you see fewer substructures and a smoother stellar halo in the warm dark matter. By eye, picking up the differences between the CDM and SIDM is harder. We'll still see some substructures in the right compared to the CDM. But I want to look at this more quantitatively. The results I will show are using simulations that Victor had run. This is a periodic box of 12 megaparsec at a resolution of about just below 10 to the 5, 8 times 10 to the 4 in resolution in gas and stars. It ran with the Eagle model, and there are 8 halos in this box. There are 8 halos with mass around 10 to the 12, which the plots I will show are based on these 8 halos. We've also looked into, we have higher resolution runs, but there are fewer halos. In Apostle local group simulations, we found consistent results, but most of the plots I will show is from the collection of 8 halos from that box. It has been run with CDM. It has been run the same, everything about the galaxy formation is the same resolution is the same, but with different flavor of dark matter. There's a warm dark matter flavor with a thermal mass of 2.5 keV, which means the abundance of halos around 10 to the 9 and below is suppressed. And there's an SIDM flavor of the run, which has a constant cross-section of 10 centimeters square per gram, which makes few kiloparsec dark matter cores in dwarf galaxies and about 10 kiloparsec cores in Milky Way size halos. You might, I agree, you might say 10 constant cross-section of 10 has been ruled out. That's true. These are the runs kind of to maybe to look at the zeroth order effect of these things, especially if the also 2.5 kV is warmer than 3.3 kV line. These are perhaps to exaggerate slightly the effect to see if we see any differences.
About a minute left.
A minute left, right, which is very little, so I have to run through the talks. First thing, we can look at the, actually I can quickly go over this. We can look at the abundance of destroyed objects in these different dark matter models. Warm dark matter is in red, lower than CDM, as expected. SIDM is slightly more, actually, because we think because this dark matter cores in the center enhances, and also self-interaction enhances the tidal stripping. So that's about the mass spectrum of accreted objects. I skipped that one. And we can look at the density profiles of objects. The dark matter, starting with dark matter, the density of dark matter, as expected, the SIDM is flatter in the center than CDM and warm dark matter. Interestingly, if we look at accreted stars, it also shows the SIDM one shows a suppression on similar scales. These are the ratios of dark matter and accreted stars with respect to CDM. At the same scale that the dark matter is suppressed, dark matter density profile is going down. Also, the density profile is going down. So
if we could wrap up, please.
Sure. And then I really have to run because I cannot go through the kinematics. We looked at the kinematics, and we saw also the anisotropy of the halos change. Because of the time, I don't have time to go through the details. What the SIDM is less radial. So this is kind of the wrap-up slide of what we've learned so far, that despite the changes that we see in warm dark matter in the low-mass dwarf galaxies, there is very little difference we see in the stellar halos. But in the SIDM, we see actually potentially observable differences in the density profile and in the kinematics. And the differences are due to different basic changes that self-interacting dark matter makes to the host and to the satellites. And I'll leave it here, and I'm happy to take questions. Sorry about rushing over the last few slides.
Thank you, Azi. All right, I already see questions.
Hi, I'm Sarah Pearson from Copenhagen. I was wondering between the differences in your SIDM and cold dark matter case on the stellar streams. When you looked at the stellar halos, it looked like in SIDM the stellar streams were thinner and maybe denser. Do we understand that in the framework of tidal stripping in SIDM?
I'm guessing you're talking about the images.
Yeah, that one.
I don't know if I would read too much into this or not, because if I was going to actually guess anything, potentially the SIDM ones, because they have a core, actually, I would expect they are a bit actually puffier, but we haven't looked at the stellar streams. The short answer is I don't have a good answer for you. We should look at the properties of stellar streams in detail. Whether what our eyes pick out here is something quite general, or maybe just one or two objects for whatever reason are thinner, I don't know.
Thanks, Azi, for a very nice talk. Ting Li from University of Toronto. So I know that the simulation you're most looking at is disrupted dwarf galaxies that are part of galactic halo. You mentioned for SIDM that there is a different density profile. I'm wondering if in the simulation there's also stellar metallicity included, and whether or not, depending on whether or not you did it, it will be a question or a suggestion is to take a look if there's any difference in metallicity distribution as a function of radius to the galactic center, and if there is a difference between SIDM and CDM.
That's an excellent point, Ting. Hi. At some point, so the short answer, yes, there are stellar metallicities in these hydroruns. And at some point we were looking at it and trying to remember, contrary to what I expected, the differences were very little. Perhaps maybe we should dig more, but at zeroth order, we didn't see any big differences in the metallicity distributions. But that's an excellent point, and we should definitely look it up again. Thanks for reminding us, or me.
Hi, Azi. This is Frank Vanden Bosch. Too bad you can't be here in person. I have a question about you pointed out that you find that the more massive satellites, their orbits get radialized due to dynamical friction. This goes counter to what I have examined some time ago. If you want to radialize your dynamical friction, basically means you need to preferentially boost dynamical friction at epicenter. So I'm trying to understand why that would be the case. The one effect that I can think of that could do something similar is sort of gravitational focusing, which means the orbits at infall are already more radial for the more massive satellites. So I wanted to know whether you looked into that and whether you really know for sure that it's dynamical friction that's doing it.
Hi, Frank. I think I know what you were asking me about this. The short answer is I've also been talking with a few kind of dynamicists who are better than me about these things, who also done kind of idealized control experiments, and none of them gave me an answer that was satisfactory, especially that by the way, just I completely agree that dynamical friction in the kind of, if you want to call it the classical regime or the general, it should circularize the orbit actually rather than radialize. It's when it gets close to 1-to-1 merger, it doesn't have to be 1-to-1, but around 1-to-10 or so, or higher mergers. Basically, various people have looked at this, that the end debris is more radial than the initial objects that came in. So I think that has been shown. But what exactly is happening, I think, is not fully understood. It also has been shown that it depends if your dark matter densities are much steeper than NFW. Actually, this radialization is not as efficient. Or if they're cored in the center, it's not also that efficient. I think it has to be in some sort of a medium in where your density in the center of the halo is high enough that kind of the center of the mass moves with respect to the rest of the halo, and something kind of messy happens after that. I think that's the word I can use. I don't have a better word for that. But sorry, I'm just waving my hands and saying things. The short answer is I don't think it's fully understood what exactly is happening, why it radializes. Is it a torque from the objects, the center of mass moves with respect to the rest of the objects and it gets torqued? Someone say it's because the sloshing of the two objects in the last few orbits close to each other makes them lose energy. But that's also, I think, these are hand wavy. These are the explanations I've heard.
Great. Thank you. Thank you.
Hi, Azi. This is Saunak from Durham. So I was curious about the point you made about the reduced number of destroyed galaxies in the warm dark matter case, because I might have anticipated that because the infall concentrations are lower, these would be enhanced in terms of disruption. So I was wondering if these numbers are normalized to the fact that the mass function is already suppressed in warm dark matter compared to CDM, and so rather than the absolute numbers being lower, if you understand what I mean.
No, I know what you mean. I was actually trying to compare this because from at least the same sets of simulation, if one looks at so this is the dark matter halo mass function of field objects, or not satellites, and well, you can see the suppression of warm dark matter with respect to CDM. The plot I showed definitely is not normalized. These are absolute numbers. So even in terms of absolute numbers, it's lower. I agree that the lower concentration is likely means they are being stripped more efficiently. Unfortunately, this is in velocity space. The other plot was in mass space. Of course, one can convert one to the other. But I think basically if one the warm dark matter ones get stripped more efficient, but it's still perhaps not, there's not enough of them anyway, so they can never go on top of CDM. I think if we normalize it by how efficient they get stripped, I think the warm dark matter one will get more efficiently stripped. I hope I answered your question.
All right, let's give Azi another round of applause for a wonderful talk.
Thanks, everyone.